In the last class, we talked about the very simplest molecule for covalent bonding, which is the hydrogen ion, H2 plus. In this class, we're going to talk about neutral atoms and give an overview of all of the various types of bonding that could be important, that are important. And those include covalent bonding, ionic bonding, van der Waals bonding, um, and because we're going through so many ideas, this is going to be more of an overview with plausibility arguments than hard numerical arguments. Um, the primary reference for this material is Crane. Essentially all of Chapter 9 in Crane, that's the principal place. For more detailed calculations, Iceberg and Resnick, of course, is a good source. I've recommended that to you before. So last class, we finished up on multi-electron atoms, and we talked about quantum tunneling, that is covalent bonding, with the H2 plus ion. This class, we're going to start out talking about the neutral hydrogen molecule, and then various types of covalent bonding, ionic bonding, metallic bonding, van der Waals bonding, and then some of the observations that we make as a result of the bonding of atoms to one another in molecules. The neutral hydrogen molecule, we start out by just asking what are the important considerations that we might have. There are going to be two positive ions and two electrons, so it's going to be neutral. The question is, what wave function do the electrons sit in? And I'll make an initial claim, which is that because the two electrons are going to attempt to get into a ground state for the system, that would be the lowest energy of the system, they'll be in the same state, and as a result, the electrons would most likely want to be in an antisymmetric spin state, spin up, spin down, if they're going to occupy the lowest state. However, if the lowest spatial state were antisymmetric, then the spins would be symmetric. We're going to find that the lowest energy spatial state is the symmetric state. The molecule will be stable if the molecular energy is lower than the energy of the two separated molecules, 13.6 electron volts binding energy per atom. Busy slide, but actually this is a repetition of what we talked about last class. That is that we make as a reasonable guess to start out with that the final wave function is some linear combination of the original atomic wave functions. That is, that it's essentially an electron on one atom and an electron on the other atom combined suitably to make a joint wave function for the system. So the overall wave function then is going to look fairly familiar to us. It's going to be the spins in an antisymmetric state, which permits the space wave function to be symmetric. Electron on one atom, electron on the other atom, and then we switch the two electrons on the two atoms. Then, as we did for the hydrogen ion, we take this wave function and put it into the Born-Oppenheimer Hamiltonian, where we're ignoring the motion of the nuclei, for now at least. And this time around, though, we permit the two electrons, we have the two electrons interacting with one another. So kinetic energy of electron 1, kinetic energy of electron 2, Coulomb binding energy of potential energy for electron 1 on atom A, let's say, binding energy of electron 2 on atom A, on atom B, on atom B, nuclear potential energy, and then the Coulomb interaction between the two electrons. In this particular case, this value here should actually be R1, R2 vector, all right? We're considering the distance between the two electrons in this system, and that yields the energy of the system. So what we could do is set the radius r, set the distance r, and then calculate the wave function rather, of the system, assuming that it's made up of these wave functions here, of the ground state wave functions of the separated atoms, assuming that it is, and then calculate what the total energy is using the same approach as we did for the ion. Okay, so we separate it into kinetic energy and overlap terms, basically, and calculate the total energy, then change the radius, change the distance between the ions, and calculate again, change it, calculate again. So we're not going to do that, of course. That has been done for us, and it is too complex a calculation to do for this course. So I've just grabbed from Crane a plot of the theoretical result for the actual computation of the total molecular energy as a function of the distance. So here's the distance between the two ions. Remember, there are two electrons in here. And the symmetric state has this property, okay? Remember, when the atoms are very, very far apart, doesn't matter whether they are symmetric or non-symmetric. So the symmetric, which is this state, and the anti-symmetric, which is this state, have the same energy at very large separation. But then as we bring them together, we find that the energy goes down for the symmetric state. And we can argue that one of the reasons that it goes down is that the wave function looks like this. That we have, there's the 0, all right? Here's atom 1, here's atom 2, and we have a choice. We have choices, all right, drawing through. One wave function is going to look like this, and the other one is, choosing another color, is going to look like that. And the red wave function turns out to have lower total energy than the blue wave function in this case. The kinetic energy is lower. That is, the curviness, if you like, of this state is greater than this state. And so the kinetic energy for the red state is going to be lower. Okay? So if we look at the overall considerations, the symmetric spatial state has lower kinetic energy to a less curvy wave function. That's good for bonding, all right? It has the two electrons overlapping between the nuclei. That's not so good, all right? But having the electrons between the two nuclei helps to screen the charge of this nucleus from the charge of that nucleus, so that's good for bonding. Overall, it turns out that the symmetric state wins because its kinetic energy is lower. As we push the two nuclei closer together, then you can think of this as making the well smaller and smaller, and as a result, the quantum mechanical energy is going to go up, the kinetic energy is going to go up, and also the nuclear repulsion is going to go up. So all of those considerations lead to a minimum at a particular radius, which turns out to be 0.074, right? The actual, that radius, that distance, is smaller than the H2 plus, and that's because now the two electrons help to screen that nuclear repulsion term. There's a useful relationship that helps us to get a good approximation for what is going on in in the molecular potential, which is called the Morse potential. This is not in the textbook, but I think it's useful to know it. So the Morse potential is an empirical approximate relationship, right? It turns out to work pretty well for diatomic molecules, and it is shaped like the blue curve here, right? Morse potential looks like that. This is one form of it. There's another form that is fairly frequently used, and so you might see that. But the two terms or three terms that actually describe it are D equilibrium, which tells us something about the depth of the well. So that's the strength of the bonding. Then there's a term in A here which multiplies the radius, which tells us something about the sharpness of the well at the bottom. You can think of it as a spring constant, right? So A is the spring constant for the system, and that is how sharp the minimum is. And then there's the equilibrium distance, which would be this distance here. So for a given molecule, these terms are determined experimentally, right? A, it'll turn out, is not so hard to measure. Or rather, the spring constant is relatively easy to measure, and then from that, we can determine what the term A here is. So those are experimentally determined things. One of the ways that we experimentally determine some of these numbers here is to optically measure the energy of excitation from one of the states of this harmonic oscillator well to the next state. So we're just changing the vibrational states of the atom, of the two atoms in the molecule. And I have a spring relationship on the next page that might help a little bit with that. So molecular vibrations, all right, are again due to the two atoms sort of bouncing into and away from one another and being bounced out by quantum mechanical forces and Coulomb forces and being pulled back in by quantum mechanical bonding, right? So what we know is that if we have a vibrating system with a mass on a spring, then it's going to oscillate at a frequency which is related to the spring constant K. A quantum mechanical oscillator is permitted to have discrete energies that you learned last semester. So there are discrete energies for the oscillator, but omega here, that omega is actually the same as the classical frequency. Perturbation theory, like what we did, tells us that the dipole selection rule is that the change in level is plus or minus 1. And so now we can actually measure the absorption frequencies for a diatomic molecule, and from that we can determine the effective spring constant, and then from that we can determine the ratio of that parameter A to the depth of the well, the depth of the oscillator. Another consideration is that for a diatomic molecule, we would consider the mass to be the reduced mass of the two atoms in the molecule. So the constants in the Morse potential are actually measured experimentally. They're very hard to determine with ab initio calculations. But then after you know what the number is, then theorists justify it. The actual relationship, in order to figure out what's going on, the relationship between A and D and so on, all right, is to start out here with the frequency of the quantum oscillator and the Morse potential. And what we're going to do is approximate this Morse potential as using a Taylor expansion. And here are the first two terms in the Taylor expansion. it turns out that the first term is 0. Well, it should be 0 about when expanding about the equilibrium distance, because the potential goes down to a minimum at the equilibrium distance. So first term is 0. That just leaves the second term, which I've written out here, taking all of our derivatives, right? Which tells us that the constant k is directly related to the a in our expression here, as well as the depth of the well. So from measuring the frequency, we get that product. So far, we've talked about bonding with 1s orbitals, but multi-electron atoms have got other orbitals as their valence orbitals. So, for example, silicon has got p electrons as the highest energy electrons in the system. So we should stop. Actually, carbon is a better example here. We should stop and ask, okay, what happens when we make combined molecular orbitals out of atomic p orbitals? Well, we can combine p orbitals in two ways. We can align the p orbitals that are bonding in bonding and anti-bonding, symmetric and anti-symmetric state here, all right, along the axis of the orbitals. Or we can align them so that the direction in which the atoms approach one another is perpendicular to the axis of the orbitals. This type of bonding is called sigma bonding, and this type of bonding is called pi bonding. So there's a sort of a sketch over here again from Crane that shows that if you have covalent bonding in which the primary orbitals, the valence orbitals, are 1s, then you just get a bonding and an anti-bonding orbital. And we saw the rest of this plot here where it sort of looks like this, but the separation is bonding, anti-bonding, just a pair, all right? And so the first two electrons in a system are going to go into the bonding orbitals. The next two electrons in the system will go into anti-bonding orbitals because of the symmetry of the spins. So as we're working our way up and we start putting electrons into a system, then the bonding orbitals will cause the pair of atoms to bond to one another. The anti-bonding orbitals, let's say I put electrons here, will push them apart. But for example, if I've only got one extra electron here, then the odds are that bonding is going to win, and I can have an ion, a molecular ion, that is actually bonded. Or if I'm short one electron, then actually we know already that it's likely that that's going to bond. Same situation if the valence orbitals are two s orbitals. The two p orbitals will extend over larger distances, so it turns out that if we bring two atoms together that have two p orbitals as their outermost electrons, the valence electrons, then those are going to interact with one another. The overlap is going to be greater for p orbitals than it is for s orbitals. So the p orbitals are going to dominate the bonding of the situation. The sigma orbitals will always be at lower energy, the symmetric state, which is sort of less curvy. And I might mention here that we noticed last year that Crane has actually got this state mislabeled. This state should also be sigma. It should be sigma, sigma, pi, pi. P orbitals can bond on one atom, can bond with s orbitals on another atom, and here are some examples. As far as covalent bonding is concerned, HF, but we're going to be worried about ionic bonding here as well. We'll come back to that in a little bit. Water is covalent and ionic at the same time, but here's the overall idea that I have a pair of p orbitals on the oxygen. Remember, there's a third, but there's a pair here that each one of them bonds with a hydrogen molecule. So we'd expect a hydrogen atom rather. So we would expect that perhaps these two orbitals are going to be at 90 degrees. In fact, the angle is a little bit larger than that because of repulsion of these two hydrogens. And here's another example of P to S bonding. 3 hydrogens, they've got the 1s states, and each of them comes in to interact with one of the orbitals of the p orbitals on the nitrogen. We can also have within a single atom what are called hybrid orbitals. That is, that it may turn out to be energetically favorable when interacting with other atoms for an atom to put electrons into a combination, a linear combination of s and p orbitals, for example. Same with p and d and so on, all right? But I've just chosen sp hybrids right here. There is a linear sp combination, which I've written here for just combining 2 orbitals. But if I take two p orbitals and 1 s orbital, then they will combine in order to make a hybridized orbital for the pair sp. It's called sp squared or sp2, where the lobes, the greatest density of electron on these ions, on the atom. So this is a single atom that has been driven into hybridization by its interaction with nearby atoms. Okay, it might turn out that this is a lower energy state. Same here, that through interaction with nearby atoms, a particular atom may find it advantageous to go into a mixed sp state, and in this case the sp orbitals are all in a plane and they form 120 degrees from one another, and this is pretty close to the bonding that is found in graphite, carbon and graphite. And then the third type of sp mixing is sp cubed, where the s orbital mixes with all 3 of the p orbitals, and it turns out to form a tetrahedron with 109.5 degrees, it's actually 0.4 degrees between lobes of the electron density, and that's called sp cubed. And this is the structure that forms diamond. So carbon can make sp squared hybrids, which put the atoms in a plane, or nearly in a plane, and it can make sp3 hybrids, which put the atoms in to form tetrahedra. Silicon and germanium and carbon diamond all have this structure, but also molecules, simple molecules have this structure. So here's methane. Structure of methane is sp3 hybridized. The next type of bonding is called ionic bonding. And ionic bonding is the transfer of an electron from one atom to another, and then the consequent Coulomb attraction. Right? Any system in which we have 2 different atoms is going to involve shifting of electronic charge on average from one atom to the other. But on the average, it might not be the entire electron charge. So there are some atoms that are quite ionic in that the electron really ends up going from one atom to the other, and then the 2 atoms are attracted to one another by Coulomb forces, but the electron still pretty much stays on one atom rather than the other. And then there are systems like water, for example, where the electron transfers slightly, spending more time on one atom than on the other, but there's also covalent interactions. So almost everything is a mixture of covalent and ionic bonding. We can estimate the bonding energy through using 3 steps. One is that we take an electron from a neutral atom. That requires energy. So it costs us. It costs the system energy to take the electron off that atom. Then that electron can be attracted to another atom. And in general, actually, whenever an electron approaches a neutral atom, there will be an attraction. It might not be a strong attraction, but there will be some attraction because the atom will polarize with the arrival of the electron. So you get some energy back. But then the thing that actually causes ionic bonds to be energetically favorable is that after we've made this exchange, then the 2 ions are attracted to one another because they've got opposite charge, and that reduces the total energy of the system. That's shown, actually I'll show that in a couple of slides, but right now we'll just look quickly at the pattern of the energy that it takes to remove an electron from a system. Okay, it takes a lot of energy to remove electrons from rare gases, from inert gases. It takes very little energy to remove an electron from a 2s orbital that's outside of the valence of the previous shell. So we've looked at that with multi-electron atoms, and here's the pattern that we know. Easy to remove electrons from lithium, sodium, potassium, rubidium. So halides, alkalis, and harder to remove electrons from rare gases, and the next thing down here are the halides. So alkali, halide. Okay. What about attracting an electron to a system, right? How accepting of a new electron is. We learned this again in our discussion of multi-electron atoms, that an atom which comes into a nearly complete shell, right, is going to have a wave function that is not fully shielded by the other electrons in the system, and as a result we'll see the nucleus and be bound. Right. Unfortunately, the best graph that I could find of this was a chemistry graph. So the energy here is in kilojoules per mole, and I just had the conversion here. 1 electron volt is about 96 kilojoules per mole. So that's about 3 electron volts. So the scale for the previous graph and for this one is approximately the same, in the sense that this is around 3, but if you looked at it for the energy that it takes to remove an electron from sodium, that's about 5. And that you'll see fairly soon. What do we think about when we're figuring what the binding energy in an ionic model might be? That first we would separate these 2 atoms and move the electron from one atom to the other. And I will tell you, most of the time that's unstable. That is, that you just don't find in nature, in the in vacuum, that a sodium atom has transferred a charge to a chlorine atom just because. All right. What they have to do is actually get together so that there is a Coulomb attraction. But if they move too close together, then there'll be quantum repulsion. In order to do the full calculation, we should use some Hartree-Fock type approach. Start with the outer electrons, find a bond length that minimizes the energy, solve for all the core electrons. It's a very involved and difficult calculation. But we can make approximations using linear combination of atomic orbitals. We're not going to do that here. These are just things that we think about. So what about the overall energetics of this situation? Here's what we know from the tables that we just looked at. The energy to remove an electron from sodium is 5.1 electron volts. The affinity energy, that is, how much energy do we get back out when an electron is added to chlorine to make chlorine minus, so we've made sodium plus to make chlorine minus, is about 3.8 electron volts. That means that it costs about 1.3 electron volts in order to move an electron from sodium to chlorine. Not good, all right? But for the sodium chloride ion, the interatomic distance between the two atoms is about 0.24 nanometers, 2.4 angstroms. Put that in to calculate the potential energy, all right, at that distance, and we get back 6 volts. All right. So now we know these two, with these three considerations, sodium chloride will be a tightly bound molecule. All right. I've got a cost 1.3 electron volts to separate the charge, but then I get 6 back. So the binding energy for sodium chloride, according to this, would be around 5, all right, 4.5. We do have to make an additional correction because in this system, we've got, when we put these two ions so close to one another, the electrons on the ions actually repel one another, and the nuclei repel one another, even though overall the ions have opposite charges, but when they get close enough together, they're going to repel. And the energy that costs is about 0.9 electron volts when you do the calculation. So the total binding energy comes out to be 3.6 electron volts. Here's a graphic of this. If I start with neutral sodium and chlorine, let's call that energy there, okay? And it costs 5.1 electron volts to remove an electron from sodium to make sodium plus an electron. Now I've got neutral chlorine here. I put this electron onto the neutral chlorine and I get back 3.8. So now it's sitting here, all right? The pair of them, well separated, sits at this energy. But if they move close to one another, their energy goes down via the Coulomb energy, continues to go down, all right? Would go through the floor, except for quantum mechanical and Coulomb repulsion when the electrons overlap one another of the core. And so that represents the minimum here. By the way, you see here that this sort of looks harmonic as well, and we can measure the shape of this well again using infrared spectroscopy. We look at the frequency of oscillation of the sodium and chlorine with respect to one another, and that tells us something about the shape of this well. As I mentioned before, we can have bonds that are a mixture of both ionic bonding, where an electron has been traded, and covalent bonding. And you see even here, sodium chloride, which we were just talking about, turns out to be about 80% ionic, and then covalent bonding accounts for the last 20% here, all right? The most ionic is sodium fluoride of the atoms that we have looked at here. And then carbon disulfide, nitrous oxide, these are all much more covalent in their bonding. And one way to sort of guess what the amount of ionic character there is to look at the difference in electronegativity on the chemical tables for different materials. Large difference in electronegativity leads to a more ionic bonding in the system. There's one more type of bonding that we're going to talk about here. I'll come back to metallic bonding later on in solid state physics because that involves a macroscopic solid, right? So van der Waals bonding is sort of a neat thing, and you'd think it would be completely unimportant. But it turns out that for many systems, in particular, like one obvious one is inert gases, liquid argon, for example, is held in its liquid state by the van der Waals bond. And inert gases have their primary interaction with surfaces via van der Waals bond. And the bonding between layers of graphite is van der Waals. So it's frequently found in nature, even though it's actually a very weak and unusual bond when you think about the physics. So here's the physics. We start out with a nice symmetric atom, and because that atom is sitting in a bath of thermal radiation, it can gain a momentary dipole moment due to a mixture of two states. By this thermal radiation causes two states in the atom to mix a little bit, with the result that we have a dipole moment. That dipole moment gives rise to an electric field which travels out from the atom. So let's our atom is here, then the electric dipole field is going to look like this out here. So out here, there's a weak electric field due to that dipole, which is over here. That dipole field interacts with a nearby atom, which might be over here, and causes it to polarize. When they polarize, the other atom polarizes, it creates a field which interacts with the first atom again. So the two atoms are interacting with one another. One of them spontaneously polarized with a weak polarization. It causes the other one to polarize. Then the polarization from this one strengthens the polarization in the first one. And that interaction is an attractive interaction which pulls the atoms together. Here's a scaling argument. The dipole field drops off as 1 over r cubed. So if we have a field, it drops off as 1 over r cubed. And the second atom polarizes in the field relative to that 1 over r cubed. And then the energy of the second dipole depends upon its dipole moment as it polarizes. And the bottom line is that the change in energy of the system due to the joint polarization of the two atoms varies as 1 over the distance between the two atoms to the 6th power. When you look at the magnitude of that energy, it's pretty small, between 1/1000th of a volt and 10/1000ths of a volt. Remember that the bonding energy for covalent bonds is of order 1 to 10 electron volts. For ionic bonds, 1 to 10 electron volts. This is 1/1000th of that, but physically important. The van der Waals is approximated, and again, this is an experimentally determined term, by what's called the Lennard-Jones potential, and it's very frequently called the 612 potential. And it consists of two terms. One is the interaction of the electric dipole fields with the atoms, the polarization of atoms under field, which depends upon 1 over the distance between the atoms to the 6th power. And that's attractive, so we put it as negative. And the other one is the quantum mechanical Pauli exclusion repulsion, that the atoms don't want to sit on top of one another. So they're pulled together by this power, and they are pushed apart by this one. As an approximation, experimentally determined for rare gases, this N is 12, right? So it's called a 612 potential because pushed apart by the 12th power of 1 over r and attracted by the 6th power. These quantities that go in here, sigma, so that's a scaling distance, is about 3 angstroms, 0.3 nanometers for rare gases. And the energy for bonding, the scale of the energy, is around 10 to the minus 2. So that's, again, an experimentally determined potential, which, if you look at the shape of this potential, it can be approximated as a harmonic oscillator for small oscillations, and you can measure you can measure the frequency using infrared or Raman scattering.